In this tutorial we're looking at section 8.3 on linear substitutions. Now if you've been having a little bit of a look at the textbook with this, you'll see that it looks pretty hard. They go through all this substitution stuff early on, which is really a waste of time to start off with, to be honest, because they then generalise our results and we get some really nice formulas that we can just use. And it'd be madness to do it the other way because you've actually seen these results in methods anyway. Okay? And our results are, if we integrate ax plus b to the power of n with respect to x, then it simply becomes ax plus b to the power of n plus 1 divided by a times n plus 1 plus our c. So the coefficient of our x also comes down and multiplies by our n plus 1. Okay, now this only works when n does not equal negative 1. Okay, when n equals negative 1, what happens is we say we get 1 on a, so again our coefficient of x, log to the base e of the modulus of ax plus b plus c. So that's when n is equal to negative 1. Okay, so I won't worry about the substitution stuff for these ones. The reason why they've done it is because we do need it for some ones later on, but let's not muddy the waters, let's keep it simple when we can. So the first one that we're doing is we've got to anti-differentiate 1 on 5x plus 4. So we're 1 on 5x plus 4 with respect to x. Okay, so we can write that as 5x plus 4 to the power of negative 1 dx. Okay, so we're going to be looking at this form. Okay, our coefficient of x has to come out and be 1 on 5 log to the base e of the modulus of 5x plus 4 plus c. Okay, far easier than that worked example done using our substitutions. Okay, so you can see that's worked example 10. If you have a look at that, it's far more complicated than what we've just done. When we have a look at worked example 11, hey, we've got our terminals in for this one. Okay, and we'll also, so we'll need to actually rewrite this as 4 times 3x plus 2 to the negative 2 dx. Now we can think of that with our 4 out the front, of 0 to 1 of our 3x plus 2 to the negative 2 dx. Okay, and that's going to be one of these cases here. Okay, so we're going to get 4 outside of, well, it'll be our 3x plus 2 to the power of negative 3. Okay, and we're going to divide it by, well, it's negative 3 times by our coefficient of x, which is 3, which gives us negative 9. Okay, and that's from 0 to 1. Okay, so we say we've got 4 then outside of our 3 times 1 plus 2 to the negative 3 over negative 9 minus our 3 times 0 plus 2 to the negative 3 over 9, negative 9, sorry. Okay, so what I'll do is I'll come up here. Okay, so really we can say that we've got 3 times 1, okay, which is 3, plus 2 is 5. Okay, so we can say really that we've got our 4 outside of 1 over negative 9 times 5 cubed. Okay, is there a better way of saying it? Minus we've got 1 over negative 9. 3 times 0 is 0, plus 2 is obviously 2 cubed. Okay, so when we do that, we've got 1 over negative 9 times 125 minus 1 over negative 9 times 8. Okay, so this is our worked example 11. So, and when we get to that, so I'm just going to keep running through. When we do all our arithmetic with that, then what we end up with is 2 on 5. When we run through all our arithmetic with that one. Okay, so just to save a little bit of time, I won't worry about that arithmetic. Okay, so we'll keep moving on. Okay, and look at finding integrals using back substitution. So this is where we do need to do a little bit of work. Okay, so for this one, what we're going to do, okay, is we're going to say let u equal 2x minus 5. Okay, so that means then our integral becomes x times u to the 4 dx. Okay, is what that means. Okay, but we can say, we've got our u, what we can say is du dx, okay, our derivative of 2x take 5 is equal to 2, okay, which means dx on du equals 1 on 2, which means dx equals a half times du. Okay, and we'll get back to how we need to use that. Now up here, okay, what we're going to do, okay, is we're going to rearrange this for x. Okay, so we're going to say, well, 2x equals u plus 5. Okay, so x equals a half u plus 5. Okay, so now we'll bring everything together. So what we want to do now is we want to modify this. Okay, because we can't find our integral with respect to x when we've got u's in there. We can't find our integral with respect to u with x's in there and with a dx there. Okay, what we know though is we can replace this dx with a half du, and we can replace this x with a half u plus 5. Okay, when we do that, okay, we're going to get our integral of a half times u plus 5, okay, times our u to the 4, okay, times a half du. Okay, replacing our dx with our half du. Now we can make that look a little nicer. A half times a half is a quarter, so we can bring a quarter out the front. Okay, and then we can multiply through by our u to the 4, okay, to make it u to the 5 plus 5u to the 4 du. And all of a sudden, this looks quite nice. Okay, so because we can say, well, that's equal to a quarter, okay, outside of u to the 6 on 6 plus it'd be u to the 5 on 5, but we've got our 5 here, so that's going to cancel out. Okay, plus our c at the end. Okay, so what we can say is we've got u to the 6 on 24 plus u to the 5 on 4 plus our c. Okay, and that's how our back substitution works. Okay, so what we're doing is we're doing our substitution for u, okay, finding our derivative of u with respect to x and rearranging to get dx so we can replace our dx up here. Okay, we've also rearranged our u for x so that we can replace our x in here. Okay, so we'll have a look at another worked example, okay, which is part B of worked example 12. Okay, and we're going to integrate 6x take 5 over 4x squared take 12x plus 9. Okay, and what we can do with this is we can say, well, if we were to factorise the bottom line, okay, we get that's 2x take 3 squared dx. Okay, so a little bit tricky to actually spot that you need to do that, but it works. Okay, and then what we do is we do our let u, and this time we're going to do our 2x take 3. Okay, so in a similar vein before, we need to do du dx because we want to replace this dx, right? And that's going to equal 2. Okay, so then our dx is going to equal a half du again. Okay, we also know up here when we want to get x by itself, we're going to say 2x equals u plus 3. So x equals a half times u plus 3. Okay, and if we have a look at our original integral up here, okay, oh now sorry, I actually mucked up there, that step, sorry. And you'll see why in just a second, okay, Because what we want to do is we want to be able to get rid of our 6x take 5. Sorry, so what we need to do is actually times this by 3 this time, and make it 6x equals 3u plus 9. Okay, so that means that our 6x take 5 is going to be 3u plus 4 instead if we take 5 from both sides, because now we've got a substitution that we replace our 6x take 5 with our 3u plus 4. Okay, and now when we do all that, you'll see that our integral becomes quite nice, because now we've got our substitution to do for our 6x take 5. That's our 3u plus 4 over, well, we did our substitution for u here, so we can say it's just u squared. Okay, and we can also say that we can replace our dx with our half du. Okay, so we can then say that we've got a half outside of our integral of 3u on u squared plus 4 on u squared du. So what I've done is just split that into our two different fractions, because that's going to work out quite nicely for us, because we can say it's 3 on u, okay, plus 4 on u squared du. Okay, so then we can say, well, we're a half times outside of our integral of 3u to the negative 1 plus 4u to the negative 2 du. Okay, so when we integrate that one, okay, well, it means that we're going to get a half outside of, well, we're going to have 3 log to the base e of the modulus of u, okay, minus, because we're going to go u to the negative 1, okay, times our 4 will give us negative 4u to the negative 1, okay, plus c. So we can make that look a little nicer. We've got our half outside of our 3 log to the base e. Now we know that u is our 2x minus 3. Okay. Take 4 over 2x minus 3, okay, plus our c. Okay, so we can just run our half through now and say, well, that's going to equal 3 on 2 log to the base e of the modulus of 2x take 3 minus, well, our half can cancel out with our 4, okay, to leave us with 2 over 2x take 3 plus c. Okay, so I've put the plus c outside of these brackets here. It actually wouldn't matter if you put inside either. The thing to remember, if you put inside and then multiply through by half, you don't need to make it c on 2. Okay, because c is just a constant. Doesn't matter if you divide it by 2, it's still a constant. Doesn't matter if you times it by 10, it's still a constant. Okay, so you can multiply and divide and things like that to c, and it's still not going to make any difference. It's still just a constant. Okay, so whether inside or outside, make sure it stays as c. Okay, so we'll keep going on. We've got one more worked example we're going to do, which is worked example 14, which we're integrating 2x on 4x take 3. So what we're going to do is we're going to do our substitution of let u equal 4x take 3. Okay, well, our du dx is going to equal 4. Okay, so our dx is going to equal 1 on 4 du. Okay, so we've got that part. Now we also need to get we want to get to 2x, so we can do our substitution in there. So we're going to say, well, 4x equals u plus 3. So 2x is going to equal a half of u plus 3. Okay, so now we've got a substitution that we can do back in here. So we can set up our integral now to finish it off. I'll do it here still. Okay, so we know that our 2x is going to equal our half u plus 3 over our u, okay, is what we've got there, times 1 on 4 du. Okay, so what we can do is we can bring this half out and the quarter out, so we've got 1 on 8, okay, outside of u plus 3 on u du. Okay, so we're getting there. Okay, what we can do is then we can say 1 on 8 outside of, let's split this up and make it u on u. Well, that's 1 plus 3 on u du, which we can say 1 on 8 outside of 1 plus 3 u to the negative 1 du. That'll come up here now, which means we've got 1 on 8 outside of, well, 1 just simply goes to u plus 3 log to the base e of the modulus of u, because it was to the power of negative 1, plus c. Okay, so we can substitute our u, oh actually we might run our 8 through, so we can say we've got u on 8 plus 3 on 8 log to the base e of the modulus of u plus c. Now we can simply sub in our u value now and say, well, we've got 4x take 3 on 8 plus 3 log to the base e of the modulus of 4x take 3 on 8 plus c. Okay, if you like, you could put that over the one fraction, but there's not too much need. Okay, and now in the textbook too, I'm not going to go through it, but there's also a second method for this worked example, and that simply involves actually doing your division of polynomials on this to split it into partial fractions, and then from there you can go through and you'll end up getting the same answer. Okay, so they are actually equivalent, our two answers that you see in there, even though they do look slightly different. Okay, so that's all there is to it in this section. So again, early on, I would ignore the linear substitution. You've got the general formulas that we can use. We've seen them in methods, so why change it now? But when we do need to do a substitution, remember the process is do a substitution for u, okay, find the derivative, okay, and rearrange that to find dx, so you've got a substitution in terms of du. Rearrange u in terms of x, and you just need to get that in the form that you need to do a substitution in. Sometimes it's for x, 2x, before we had 6x take 5, so there's a few different ways. Okay, sub everything into your integral, okay, rearrange, make it a little bit nicer, do those things that you need to, and then actually do your integration. So look, there is a pretty nice process that you can follow for a lot of these questions, so you need to just make sure that you're following that process, and you should get through the questions with hopefully not too much difficulty.